Segway Modeling by Cadet Young, Cadet Galbraith, and Cadet Blanchard. Our research questions. What are the parameters for a PD controller required to keep an average human up on a Segway? Our other research question was, what is the minimum values of KP which will bring the pendulum to the upright position? Our solutions. We can model the motion of an inverted damped pendulum using this function. The solution to this equation under the given initial conditions of sigma 0 equals 0.001 and sigma prime of 0 equals 0. This graph shows that sigma t is the angle of the pendulum while t represents time. The function under the given initial conditions shows that the angle oscillates over time as it finds its balance where the function evens out, so the slope approaches 0, showing that t equals 30 and sigma t equals 3. The inverted pendulum stands upright. So now we can show the motion of the pendulum subject to the PD control with the equation. Using the same initial conditions, and Kp equals 20 and Kd equals 1, we can see that the added control causes the pendulum to oscillate at a greater range of angles and a lower speed. At time equals 6, the pendulum stands up straight and maintains its balance, as you can see in this graph.
We can show the motion of the pendulum subject to a PD control with this equation. We used the same initial conditions and K of P equals 3 and K of D equals 1 as our control. Using this new control causes the pendulum to oscillate less than the previous control, forcing the angle to stabilize at a slower time, but with less angle variations. This shows that the control system with a lower K of P value has more of an impact on the balance of the system, as at t equals 9, the slope approaches 0. However, the angle does not approach 0, meaning it does not stabilize in the upright position. These graphs attempt to find the minimum K of P value that will balance out the Segway, meaning the Segway stands in the upright position. The without control graph shows that there is no PID control to stabilize the pendulum, and this causes it to oscillate before approaching stabilization at t equals 11, but it does not approach 0. The with control graph uses a K of P value of 4.9 to stabilize the pendulum. The value allows for the pendulum to stand in the upright position, alpha of t equals 0, quickly without the user experiencing oscillation of the angle to the ground before standing upright. We found the value to be 4.9 because any lower value causes the pendulum to not approach 0, and any higher value causes the pendulum to oscillate. The top graph has a pendulum with a smaller L value. L equals 2.4 meters, which makes the pendulum smaller, while the bottom graph has a larger L value. L equals 25 meters, resulting in a larger pendulum. This shows that the smaller the pendulum, the less time it takes for the graph to hit alpha of t equals 0, indicating that the system has reached an equilibrium. The smaller pendulum hits equilibrium at approximately t equals 32, and the larger one hits at approximately t equals 50. The mass used for these solutions was 62, since 62 kilograms is the average weight for adults.
These graphs can be transferred into a real-world situation. So in the real world, the Segway scooter can be modeled by this pendulum, which is what we just saw in the graphs, and that's subject to the PID control that allows for the balance, so that meaning the Segway can stand up straight. Before the control was applied to the graphs, it oscillated before eventually approaching 0. And this relates to real life because when you turn the Segway on, it'll sway back and forth before it's able to stand upright. And then once you apply the PID control, the pendulum stabilizes and approaches 0 very quickly, similar to how when you turn on a Segway now, it just stands up and it doesn't move. And then you can use the results from question 7 to show that the Segway needs to have a shorter length so it can stabilize, which is most likely due to the shorter length having a lower center of gravity, so it's able to balance easier. And then for the considerations, we have to consider that the weight of the user may not be around the average that was used in equation number 7. So the PID control needs to have some quote unquote wiggle room to account for this. So different users may experience different angles and different times that it'll take for the Segway to balance out than what is shown in the data. If this model were to be recreated, we would use different masses in the equations to account for the lighter and heavier users to give us a range of solutions so that the PID control can take this range into consideration. And the current model is not very robust in accounting for different heights and weights, since the graph only accounted for the average weight that was used.